Welcome viewers to the NPTEL lecture series on the calculus of variation. This is the 10th lecture of the series. In this we will consider more general functionals. Recall that in the last lecture we had functional of the type I y equal to x 1 integral x 1 to x 2 f of x y y prime dx, and y is supposed to satisfy these boundary conditions y at x 1 equal to y 1 and y at x 2 equal to y 2. Now, we shall consider more general functional of the type I y 1 y 2 and so on y n. So, there are n functions admissible functions such that this I y is of the type integral x 1 to x 2 f of x y 1 x y 2 x so on y n x, and then their derivatives are appearing y 1 prime x y 2 prime x and so on y n prime x dx, and then these y i's are to satisfy the boundary conditions that y 1 x 1 equal to alpha 1 y 2 x 1 equal to alpha 2 and so on y n x 1 equal to alpha n, and y 1 at x 2 is beta 1, y 2 at x 2 is beta 2 and so on y n at x 2 equal to beta n. So, these are the boundary conditions for each of these y i's are to be imposed to satisfy, and so this I is function of all these n functions y 1 y 2 y n. Here x is independent variable and these y 1 y 2 y n are functions of x, and the derivatives are appearing here y 1 prime x y 2 prime x and so on to y n prime x. So, here all these y i's are assumed to satisfy certain smoothness properties, so that this integral is well defined. Now, here we would like to have this set of all these y 1 y 2 y n to satisfy certain equation. So, that that will be a kind of a necessary condition, as we had got Euler's equation in the case where I y was f of integral x 1 to x 2 f of x y y prime dx. So, similar kind of equation we would like to obtain, which will be a necessary condition to be satisfied by these n functions in order this y this functional I to have optimal value. So, we proceed in the same manner. What we do here, we vary y j only and keep y 1 y 2 so on y j minus 1 y j plus 1 y n fixed. So, we change only y j, and so we get this phi alpha as function I of y j plus alpha delta y j, which is nothing but the integral x 1 to x 2 f of x y 1 y 2 and so on y j minus 1 y j plus alpha delta y j, and then y j plus 1 and y n, and then there are derivatives y 1 prime, y 2 prime, so on, y j minus 1 prime, y j prime plus alpha delta y j prime, and then y j plus 1 prime, and so on to y n prime dx. So, the necessary condition that this y j, so y 1, y 2, y n give the optimal value of I is phi prime alpha at alpha equal to 0, must be equal to 0 in this case, this particular case, and so we get phi prime alpha is integral x 1 to x 2 f of y 1 plus alpha delta, sorry, y 1, here only we have y j plus times delta y j here plus f of y j prime plus alpha delta y j prime and delta y j prime dx. And now, as before, we shift this derivative here, and so this is equal to x 1 to x 2 f of y j plus alpha delta y j minus d by dx of f of y j prime plus alpha delta y j prime delta y j x dx. And so, hence this phi prime alpha at alpha equal to 0 implies that integral x 1 to x 2 f of y j minus d by dx f of y j prime delta y j dx. We invoke the fundamental theorem fundamental lemma of the calculus of variation to get f y j minus d by dx of f y j prime equal to 0. So, this is what we get. This, since j lies between 1 to n, is arbitrarily chosen, hence f of y j minus d by dx f of y j prime is 0 for j equal to 1, 2 and so on up to n. So, we get the system of equations for each y j, we get one equation like Euler's equation. So, this system is, so this system of second order equations, second order differential equations forms the necessary condition such that this y 1, y 2, y n optimizes I y 1, y 2, y n. And there will be obviously constants appearing in the solutions, and those constants are to be determined by the given conditions. So, we will take some examples here. So, let us, so in particular if n equal to 2, we get I y z is integral x 1 to x 2 f of x y x z x and y prime x z prime x. Here, so this, let us give this is 10.1. So, 10.1 in this case is f y minus d by dx of f y prime equal to 0 and f z minus d by dx of f z prime equal to 0. Here we have situation like this. This is x axis, y axis, this is z axis. So, here in a 3D space, let us say these are the 2 points A and B. So, this is like you have x 1, y at x 1, we will call it y 1, z at x 1 as z 1, and here x 2, y 2, z 2. So, these are 2 points here. So, this will be the curve which will be parameterized as x, y x and z x. So, any point here, typical point P will have this coordinates is x, y x and z of x. Here this, let us say this is the projection of this here like this in the x y plane. So, this is A dash, B dash. So, this is x, y x and 0. So, this is x 1, y at x 1 and 0. This is x 2, y at x 2 and 0. And if you project this on to this like this, you have let us say a double dash here and b double dash here. So, this is the curve zx curve which is in the xz plane, and this is the curve yx curve. So, here we will have in this case x and yx are there and z is free. So, it is going to be this plane like this, hypersurface rather, and here this only x and zx are here in this and y is free. So, it will give us a surface like this, and so here this curve is the intersection of two surfaces. The curve x y x z x is the intersection of two surfaces, that is here you have x and z x given and y is free. So, it goes in this direction, and here in this case you have in this surface you have x y x moving along this curve and z is free there. So, let us say this is surface S1 and this is surface S2, S1 and S2. So, that is the situation here. So, let us take this example 10.1, let us call it 10.2 now. So, here I of y comma z is 0 to 1 y prime square plus z prime square plus 2 y z dx, and the conditions are y 0 equal to 0, y at 1 equal to 1 and z 0 equal to 0 and z at 1 equal to minus 1. So, in this case f x y z y prime z prime is given by y prime square plus z prime square plus 2 y z. And so, the system 10.1 implies that f y minus d by dx f y prime equal to 0 and f z minus d by dx of f z prime is 0 gives here 2 z minus you get y double prime equal to 0 and 2 y minus 2 z double prime equal to 0. So, we have thus we have y double prime equal to z and z double prime equal to y. So, differentiating first, let us say this is a and this is b. A twice with respect to x we get y fourth derivative equal to z double prime, but z double prime equal to y, and so we get this implies that d 4 minus I of y equal to 0, or d square plus 1 into d square plus I to d square minus I of y equal to 0. And so, the auxiliary equation is m square plus 1 into m square minus 1 equal to 0, and it has roots plus 1 minus 1 and plus I minus I. So, we get y of x as c 1 e to the power x plus c 2 e to the power minus x plus c 3 cos x plus c 4 sin x. And so, y and z equal to y double prime, and so this is equal to c 1 e to the power x plus c 2 e to the power minus x, and here, because here twice derivative gives you again plus sign, here twice derivatives will give you minus sign. So, minus c 3 cos x minus c 4 sin x. Now, these c 1, c 2, c 3, c 4 will have to be determined by the given condition. So, that we use here. Now, since y 0, we have these conditions, y 0 equal to 0, y 1 equal to 1, z 0 equal to 0, and z at 1 equal to minus 1. So, we have these conditions. So, these imply so first using this, since now y x is this c 1 e to the power x plus c 2 e to the power minus x plus c 3 cos x plus c 4 sin x, and z is c 1 e to the power x plus c 2 e to the power minus x and minus c 3 cos x minus c 4 sin x. So, both these imply now that y at 0 equal to, so you get c 1 plus c 2 plus c 3 equal to 0, and z 0 equal to 0 implies z 0 equal to 0. This also implies that c 1 plus c 2 minus c 3 equal to 0, and so these two will imply simply subtracting these two by subtracting this gives us c 3 is equal to 0, and now y at 1 equal to 1 and z at 1 equal to minus 1 will imply that c 1 e plus c 2 by e plus c 4, c 3 is now 0. So, that is gone, sin 1 equal to 1, and c 1 e plus c 2 by e minus c 4 sin 1 equal to minus 1. So, subtracting we get c 4 twice of this equal to 2. So, we get c 4 equal to 1 over sin 1. Now, we see that and adding we get c 1 e plus C 2 over E equal to 0. Now, one solution is clearly we can get clearly C 1 equal to C 2 equal to 0 satisfies this. We have to ensure that this is the only solution. To ensure that, we show that this is the only solution. Since if C 1 is not 0, then clearly we get E square equal to C 2 by C 1, and hence C 1 and C 2 will have the same sign, and therefore, but then C 1 E plus C 2 by E cannot be 0. Hence, this is not possible. Hence, we have only C 1 equal to C 2 equal to 0. So, we get finally this y x equal to, thus y x equal to sin x by sin 1 and z x equal to minus sin x by sin 1. So, that is the case in this example. Now, the next example here, .3. So, I y comma z is here x 1 to x 2 f y prime z prime dx. Here the variable x is missing, and so here f x y z y prime z prime is f y prime and z prime. The variables x, y and z do not appear explicitly. So, it was in the like in the earlier case function of y prime only in the special case which we had here like this, and similarly here we have only, since now there are two dependent variables and f is function of y prime and z prime only. So, it is similar to that case or generalization of that one, and so here this system 10.1 gives that, which is actually f y minus d by dx of f y prime equal to 0 and f z minus d by dx of f z prime equal to 0 reduced to f d by dx of f y prime equal to 0 and d by dx of f z prime equal to 0. So, we now this is function of y prime and z prime, and similarly f of z prime is also function of y prime and z prime, since y is so, and therefore, opening this, expanding we get f y prime y prime y double prime plus f of y prime z prime z double prime equal to 0 and f of z prime y double prime plus f of z prime z double prime equal to 0. Now, here we would like to solve this system for y and z, and so if the coefficients satisfy this, if this into this minus this into this is not 0. So, y prime into this f of z prime minus f of y prime z prime into f of z prime y prime. If this is not 0, so then we know that the only trivial solution should hold, and so y double prime equal to 0 and z double prime equal to 0, and this implies that y equal to a x plus b and z equal to c x plus d. So, in this case you have situation like here this is a straight line like this is, and similarly here. So, this is a x plus b and this is c x plus d, and so here z is free. So, this is this vertical plane like this, and here so something like this in this. So, here the intersection. So, the curve x y x z x is the intersection of two planes, hence a straight line. So, in this case we get straight line. Now, this next example, this is from optics. Here it is asked to find the curve along which light moving with the velocity v, which is a function of x, y, z, takes the minimum time. So, this is Fermat's principle. What it says that the light passing through 2 points here, A, that is x 1, y 1, z 1, and B, x 2, y 2, z 2, moving with velocity this takes. So, the least time it takes that path. So, that here the time taken by this light ray, which is moving with the velocity v x, which is a function of x, y, z, takes the least time. So, we know that time taken by this here, then it will be function of y z, and it will be integral from x 1 to x 2 ds over the velocity this v x y z. And now ds, we know that in 3 dimension it is square root dx square plus dy square plus dz square over you have v x y z. Now, if we take x as parameter and y as a function of x and z as function of x, then we see that this is x 1 to x 2 square root plus 1 plus y prime square z prime square dx comes out and v of x y z. So, it is of the type what we have been considering, and so here f is x y z, y prime z prime, which is square root 1 plus y prime square plus z prime square over v x y z. And so, 10.1 implies that, which is f y minus d by dx of f y prime equal to 0 and f z minus d by dx of f z prime equal to 0 gives you here f y gives you square root 1 plus y prime square plus z prime square over minus v square and then v x and minus d by dx of 1 over v and 1 over should be y prime, then square root 1 plus y prime square plus z prime square equal to 0. So, we can multiply by minus and we make it plus here. Similarly, the second one will give, sorry, this should be y derivative v y. So, square root of 1 plus y prime square plus z prime square over v square and v z plus d by dx of 1 over v z prime over square root 1 plus y prime square plus z prime square. So, this is the system which should be satisfied by the velocity v and y prime and z prime. So, in order to get y and z, we solve this system to get the extremals. Now, next we will consider when higher derivatives are appearing, f involves higher order derivative So, here it will be like I of y x 1 to x 2 f of x y x and then y prime x and so on up to nth derivative x. Still it is not general, the next one will be where these y 1, y 2, y m are appearing and their higher order derivatives are also appearing. So, first we tackle this case. So, here this y and its derivatives up to n minus 1 must satisfy these conditions. Y at x 1 is alpha 1, y prime at x 2 x 1 is alpha 2 up to y n minus 1 at x 1 is alpha n and y at x 2 is beta 1, y prime at x 2 is beta 2 and so on to y n minus 1, x 2 is beta n. So, we would like to see what are the conditions being satisfied by this y in order this I to have optimal value. So, here we proceed in the same manner, we consider this phi alpha like this, which is I of y plus alpha delta y, and so this is equal to integral x 1 to x 2 f of x y plus alpha delta y and y prime plus alpha delta y prime and so on, y n plus alpha delta y n dx. And so, differentiating it with respect to alpha, we get x 1 to x 2 f y plus alpha delta y to delta y plus f of y prime plus alpha delta y prime, and so this with respect to alpha will leave delta y prime and so on, plus f of y n plus alpha delta y n to delta y n dx. And proceeding in the same manner, shifting these derivatives onto f will give us this x 1 to x 2 f of y plus alpha delta y minus, and so delta y will be really raised from here, that will take out, and so we will have d by dx of f y prime alpha delta y prime plus d 2 by dx 2 f of y double prime plus alpha delta y double prime minus plus so on, plus the last term will be minus 1 to the power n d n over dx n f of nth derivative y n plus alpha delta y n delta y x dx. And so, now the condition is f prime alpha at alpha equal to 0 must be equal to 0, that is the necessary condition, and so it implies that x 1 to x 2 f y minus d by dx of f y prime plus d 2 by dx 2 f y double prime and so on, minus plus and minus 1 to the power n d n over d x n of f y n delta y x dx equal to 0. So, the fundamental lemma of the calculus of variation implies that f y minus d by dx of f y prime plus d 2 by dx 2 f y double prime minus plus so on plus minus 1 to the power n f y nth derivative is 0. So, this is what is called the Euler-Poisson equation. So, Euler-Poisson equation is the necessary condition for y to have the optimal value of the functional. So, here let us consider some examples. So, this example is now, let us see what we had earlier, 10.4. or rather we will put it this one as 10.5 and this as 10.6. Here we consider I y is 0 to 1 plus y double prime square dx. So, the conditions are y 0 0, y prime 0 is 1 and y at 1 is 1 and y prime at 1 is also 1. So, this 10.5, that is Euler-Poisson equation 10.5 implies in this case f y minus d by dx of f y prime plus d 2 by dx 2 of f y double prime, because here n equal to 2. So, we get that, and here since f is f of x, y, y prime, y double prime is 1 plus y double prime square here, and so we get this y is not appearing explicitly. So, we this term is 0, this term is also 0, only we get y fourth derivative equal to 0, and so we get y x as, so it should be a polynomial of third degree. So, it should be of the form a plus b x plus c x square plus d x cube. Now, these a, b, c, d will have to be determined by the given conditions. So, y 0 is y 0 equal to 0 implies that a equal to 0, and y prime at 0 to 1 implies now y prime x is a is 0. So, we get b plus 2 c x plus 3 d x square. So, this will give us 1 equal to b plus okay. So, b is 1 because now other thing. So, b is 1 and so now y is x plus c x square plus d x cube now, and so the other conditions that y at 1 is also 1. So, we get 1 equal to 1 plus c plus d. So, this implies that c plus d equal to 0, and the last one y prime 1 equal to 1 implies that 1 equal to 1 plus 2 c plus 3 d equal to 0. So, we get 2 c plus 3 d equal to 0, and this would imply that c equal to d equal to 0. So, we get finally y x equal to only c is 1 only y equal to only b equal to 1 and other things are 0. So, we get y equal to x as the extremum, a straight line. In this case, as expected that whenever this function involving only highest order derivatives, we expect that the solution will be a straight line. The next one would be this example 10.7, and here this I y is see 0 to pi y double prime square minus y square plus x square dx. The conditions are y 0 equal to 1, y prime 0 equal to 0, and y pi equal to minus 1, and y prime at pi equal to 0. So, again this 10.5 implies in this case that f y minus d by dx f y prime plus d 2 f d 2 by dx 2 of f y double prime equal to 0. And so, here since f is which is x y y prime y double prime is y double prime square minus y square plus x square. So, it gives, so f y will give us minus 2 y. So, minus 2 y here and plus this there is no y prime here, only y double prime, and so you get 2 y fourth derivative equal to 0. So, we get d 4 minus I y equal to 0, which or d square plus I into d square minus I y equal to 0. And so, as before we get y x equal to c 1 e to the power x, c 2 e to the power minus x plus c 3 cos x plus c 4 sin x. Now, the conditions imply we have this y 0 equal to 1. So, this is c 1 plus c 2 plus c 3 equal to 1. That is the first condition. Then y prime 0. So, y prime will give us here. So, y prime 0 means you will have c 1 minus this minus sign will come here minus c 2, this will become minus cos minus sin x, and so it will give us minus c 3, this sin x will become cos x, and so sorry plus. So, this sin c 3 will term will not be there, plus c 4. So, let us write y prime here. So, y prime is c 1 e to the power x minus c 2 e to the power minus x minus c 3 sin x plus c 4 cos x. So, we will get this when we put 0, you get c 1 minus c 2, this will become 0 plus c 4, and that is equal to y prime 0 equal to 0. That is the second condition. And now, at pi here minus 1. So, you get c 1 e to the power pi plus c 2 over e to the power pi minus c 3 equal to minus 1, and c 1 e to the power pi minus c 2 e to the power pi minus c 4 is 0. Now, we can see that here we get this system will have unique solution, and we can see that here c 3 equal to 1 and c 1 to c 2 equal to c 4, this is 0. It satisfies this equation because c 3 1 here and this all 0 here, this minus 1 and all these 0 So, this since this system is having unique solution, and so we can see that C 3 equal to 1 and other things are 0 gives you the solution, and we get the extremal y as a function of x as cos x. So, here we consider more general functionals. Now, in the next we will consider where more independent variables will be appearing, and we will see that we will have domains in the higher or dimensional spaces, that we will consider in the next lecture. Thank you very much for viewing this.